Okay, in this video I'm going to be determining the pH of a solution of HN3, which is a weak acid, and it's 0.2 molar, and the Ka is 1.9 times 10 to the minus fifth. The most important thing to note when you're determining the pH of a weak acid is that you need to think about it in terms of an ice table. So an ice table starts out with what happens when you put the weak acid into water. It's an equilibrium because it is a weak acid. Strong acids are reactions, they go all the way to the right hand side, but weak acids are in equilibrium. So we have HN3 reacting with water. The acid is a proton donor, the water is the base, the proton acceptor. So after the water pulls the proton off of the acid, it becomes hydronium ion, and you're left with the conjugate base of HN3, which is N3 minus. So initially, the concentration of HN3 is given to you in the problem, 0.2 molar. Water doesn't appear in Ka expressions because it is a pure liquid. It doesn't change concentration, so we don't really care about what's going on with water. Our initial hydronium ion concentration is 0. Our initial N3 minus concentration is also 0. In this case, the equilibrium is going to shift to the right-hand side because we have no products, and at equilibrium we should have some products. So the equilibrium shifts to the right. So the change is that our HN3 concentration will decrease by x. It's 1x because the coefficient here is 1. Hydronium will increase by x because its coefficient is 1. And N3 minus will also increase by x because its coefficient is 1. So at equilibrium, the concentration of HN3 is 0.2 minus x, x, and x. We're ready to plug these things into the Ka expression. Remember that Ka, the acid dissociation constant, is equal to the concentration of products. For this particular acid, we have hydronium and N3 minus to their orders, and our orders are all 1. So hydronium to the first, N3 minus to the first, divided by the concentration of the reactants, HN3, also to the first power, and water is already taken care of in our Ka expression. So we're ready to plug these values in, the concentrations at equilibrium, into our expression for Ka. To make our life easier, we're going to make an assumption that the change in x is negligible. So at equilibrium, the concentration of HN3 is about 0.2. That just simplifies the math. So now we have Ka, 1.9 times 10 to the minus fifth, equals x squared divided by 0.2. Solving for x, you get x is equal to 0.00195. It's good practice every time you make an assumption to check to make sure that your assumption is valid. So to check to make sure the assumption is valid, you take x, 0.00195, and you put it over your initial concentration, the 0.2, and multiply it by 100. If this is less than 5%, then your assumption is valid. And in this case it is, it's 0.975%. So our assumption is valid. Now if we look and see what this x really is telling us, this x is telling us what is the concentration of hydronium at equilibrium. Concentration of hydronium is directly linked to pH. So since the concentration of hydronium is equal to 0.00195 and pH is equal to the negative log of hydronium, we can just plug that x value into the hydronium concentration to get pH. So pH is equal to the negative log of 0.00195, giving us a pH of 2.71.